Hello everyone. For this lesson today we're going to discuss nuclear chemistry. One aspect of nuclear chemistry is isotopes. And I know we've covered isotopes before, but let's revisit them. And so isotopes are elements that have the same number of protons but different masses. So in other words, they have the same atomic number but a different mass number. Let's look at carbon-12, carbon-13 and carbon-14. Because it's carbon, I know that it must have 6 protons. Okay, so if I look at my periodic table, which is a bit hard to see, but you'll see that carbon has 6 protons. Okay, and this average mass of 12.01 grams per mole is averaged, and what it means is that in nature we predominantly have carbon-12, but there are small amounts of carbon-13 and carbon-14. So that 12.01 reflects the weighted average. So it takes into account how much of these isotopes there are. But the main thing is that all of them have 6 protons. Okay. If it had 7 protons, it would no longer be carbon. You would be at nitrogen, for instance. Or if it had 8 protons, it would no longer be carbon. It would be oxygen. So the mass must come from the number of protons and the number of neutrons. The electrons don't weigh much compared to the protons or the neutrons, so we look at that as negligible. So this mass number of 12 must have come from 6 protons and 6 neutrons. The mass of 13 must have come from 6 protons and 7 neutrons. The mass of 14 must have come from 6 protons and 8 neutrons. So as we've discussed previously, if you want to calculate the number of neutrons, all you do is you get the mass number, take away the atomic number, which in this case is 6, and that would tell you the number of neutrons. Let's do another example with oxygen. So say we have these 2 different isotopes, oxygen-16 and oxygen-18. How many protons and how many neutrons? Well, I haven't written down the protons here, so if you wanted to work out the number of protons for oxygen, you'd have to go to your periodic table and you'd look at oxygen and you'd see that it has 8 protons. And so then if I want to work out the neutrons, it would just be 16 take away 8. So in oxygen-16 there would be 8 neutrons. In oxygen-18 there would be 18 take away 8, which is 10. So there's 10 neutrons for oxygen-18. And so these calculations are done for us on the next page. And so it would be 16 minus 8 is 8 neutrons for oxygen-16, and 18 minus 8 is 10 neutrons for oxygen-18. Okay, the 8 comes from the atomic number, which is also the number of protons. So again, just to reiterate, as an important note, you can have oxygen-16 with 8, oxygen-18 with 8 protons, but you cannot have oxygen-16 with 10 protons, or oxygen-16 with 9, or oxygen-18 with 6, because as soon as you change these bottom numbers, or if you like, as soon as you change the number of protons, you no longer have oxygen. You now have, in this case, that would be neon, because it's 10 protons. If it was 9, it would be fluorine. If it was 6, it would be a carbon again. Okay, so let's have a look at a special type of isotope called a radioactive isotope. If we do the contraction with these two, we get radioisotope, and that's what they're commonly referred to in chemistry and physics. These radioisotopes are unstable elements, and they emit energy to form a new nucleus. And there are a few different ways that this can happen. Different types of radiation are alpha particles, firstly, which are basically a helium nucleus. So the helium nucleus is composed of a mass of 4, and it's got 2 protons, therefore it must have 2 neutrons. So a helium nucleus is 2 protons and 2 neutrons. And because we're just talking about the nucleus, there are no electrons around it. So this has actually got a +2 charge. We don't worry about writing that here, but the helium nucleus has got a +2 charge because the 2 electrons are removed. We also have beta particles that come off. Now, beta particle is just an electron, and we often write it with this symbol. Okay, so it's got a mass of 0, and this isn't saying it's got a negative proton or anything. but it's just saying that it's got a negative charge. Okay. So we have a positron, which is a positive electron. And this is something that you probably haven't come across, but like the electron, it's essentially massless, and it's a positively charged particle. It is actually antimatter. It's the antimatter to the electron. If an electron and a positron interact and collide, they release energy. But we won't go into too much detail with that. But these sorts of things are associated with the antimatter. This then brings us to gamma rays. Now, gamma rays are just very high energy light radiation. They're actually higher in energy than X-rays, and outer space is full of gamma rays. Thankfully, our Earth's atmosphere protects us from those gamma rays. Otherwise, we'd all be toast. Let's have a look at examples of how this works. Now, alpha emissions are actually quite easy to see. So say if we start off with our uranium-238, if that uranium nucleus emits a helium nucleus, then we get down to thorium-234. All you need to do is remember to subtract the numbers. So 238 take away 4 is 234. This is a conservation of mass. So the 234 and the 4 will give you back 238. Okay, it's the same as the protons. We started with 92 protons, and you lose 2 via a alpha particle emission, then you must only have 90 protons left. Okay, so that's very easy. All you have to do is if you get the original, and you subtract the 4, and you subtract the 2, and so first of all you do that. So you wouldn't necessarily know that it's thorium at this stage, but you get the 238, take away 4, and you write 234 here. You get the 92, subtract 2 from that, and you get 90. Then what you would do is go to your periodic table and look at what element is number 90. And so if we look on the periodic table, we have thorium comes in at number 90. Okay, so uranium's 2 atoms over, 2 elements over, and thorium's number 90. And so then you'd put the TH there. Okay, so that's the way you'd work this out. So let's have a look at the question. So if thorium-223 undergoes alpha decay, what's the product going to be? Well, you would start off with writing it like this. The 233 thorium is going to release an alpha particle. So if I want to find the mass number, it's going to be 223, subtract the 4, and so that gives me the 219. Okay, and then if I look at the 90, subtract the 2 from 90, I get 88. And so that means that I then go to my periodic table and have a look at what element has an atomic number of 88. And if you look there, you'll see just near my thumb we have radon and radium, and radium's got this atomic number of 88. And so that's how I know that that's going to be the element there. And so that would be the answer. Radium 219 is going to be the product from thorium 223 emitting an alpha particle. Now beta emissions are a little bit more complicated, but if you follow this process it shouldn't be too bad. So the beta particle, which as we've discussed is an electron, actually comes from a neutron splitting up into an electron and a proton. Okay, so with that definition, let's consider carbon-14 and how it will give us nitrogen-14. So carbon-14 has a mass of 14. We know it has 6 protons from the periodic table because that's the atomic number 6. And so that means it must have 8 neutrons because 14 take away 6 gives us 8. Now, if by definition one of these neutrons is converted to an electron and a proton, the electron leaves the element, the atom, and becomes its own sort of particle. But the proton remains in that nucleus. And so now we've gone from a situation where we've had 6 protons and 8 neutrons to one of these neutrons being formed into a proton and the electron that's been ejected. And so now if you have that emission of the beta particle, we must now have 7 protons and 7 neutrons. Okay, so I'll repeat that again. We originally had 8 neutrons. One of those neutrons is converted into a proton. So now our proton number increases from 6 protons to 7 protons, and the beta particle is gone. And so because this neutron is being converted, we now have 7 neutrons. Let's have a look at that with an overall picture. Okay, so this is just sort of summarizing what I said. Okay, let's have a look at the equation. So the carbon-14, the mass is still conserved. The mass is still conserved because all we've done, if you remember, that the mass of an atom is dictated by the number of protons and the number of neutrons. The number of electrons really doesn't dictate the mass at all. So we started off with a mass number of 14. We maintain that mass number. Okay, we started off with 6 protons, but we know that one of these neutrons, so there was 8 neutrons, is going to be converted into a proton. So now we've got an extra proton. Okay, and that's basically it. So if you want to calculate the product from beta emission, all you do is you first, the procedure would be to first look at the original, and then we know that we're going to have a beta emission, and so then my next step would go, okay, I must increase my number of protons and the mass stays the same. And so I know that then my my atomic number must increase from 6, okay, up to 7. Then I go to the periodic table and have a look at what the seventh atom in that periodic table is, and that happens to be nitrogen. So then I would write my nitrogen, okay. And as I said before, the mass is always conserved in beta emission. Okay. Now let's do another example. Okay. So this question is, what is the product when strontium-90 undergoes beta emission? So in all these cases, if you were just given the element and the number like this, it's talking about the mass. It's not talking about the atomic number. And the reason you never talk about atomic number is because it's implied by the element name. So all you have to do is you go to the periodic table and you'd look up strontium, which is in the second group, okay, which is there with SR, and so you would see that its atomic number is 38. Okay, and so then you'd write down the symbol 9038. So it's going to emit a beta particle, and so it's going to emit a beta particle. So we're converting one neutron into a proton, so the mass stays the same. This is going to increase by 1. Okay, so my first steps would be to write that. The mass stays the same. This goes from 38 to 39. Then I would go to my periodic table and look at what the 39th element is. So the one that is neighbouring strontium there is the Y, which is yttrium. And so then I'd write down the Y for yttrium. Okay. So it's not too bad. Now, positron emission is similar, but almost the reverse process. So what happens in positron emission is that we have a proton in the original nucleus, and now that proton gets converted into the positive electron, which is called the positron, and which is essentially massless, and also a neutron. Okay, so I'll say that again. In positron emission, the original nucleus has one of its protons converted to a neutron and a positron. Okay, and as I've said before, we have this sort of symbol for it. Let's look at our example. And so if we start off with fluorine 18, which has an atomic number of 9, which means it's got 9 protons. Now, according to our definition up here, one of these protons must be converted to a positron, which is this particle here. A positron plus a neutron. So again, our mass number is not going to change because all we've done is convert a proton to a neutron. They're about the same mass, so it's not going to change the mass. But now we have one fewer protons, so the atomic number will change. And so our first step is to look at that conservation of mass. So the 18 stays as an 18, but now our number of protons must go down because one of those protons has been converted to a neutron. Okay, so now we have one fewer protons. Then we go back to the periodic table and look up what number 8 is in the periodic table, which is oxygen. And so then I write the symbol O. Gamma emission, you'll be relieved to know, is easier. So because gamma isn't really a particle as such, it's more light that comes off. It's just high energy light. Gamma emission is sort of associated with gamma emission will occur with a lot of these processes. You see, when you have beta particle emission and things like that, it often corresponds to a gamma emission. But really, the gamma emission is because the element at the time is in an excited state, and so we write this little m for the excited state. And all it does is that element sort of high energy, and then it releases the gamma ray, and then it relaxes down to the lower energy state. And so nothing changes. You have the same mass number, you have the same atomic number. Okay, it's just that this m, which we sort of write to denote that it's excited, now just disappears. Okay, because the element's no longer excited. And gamma ray is a form of energy. Mass and atomic number do not change, and the little m indicates that the atom is excited and loses energy via the gamma emission. Okay. So let's have a look at a summary here. Now, in this summary, when you see Y, that is not yttrium. That's just alphabetical order, X, Y, okay? It just denotes some element. So if we start off with an element X with an atomic number Z and a mass number A, we have the following. So for alpha emission, so this is how we normally write the symbol. So we'd have X as the element, and A is our mass number, and Z is our atomic number. If we have helium emission, then this would be the mass number, take away 4. It would be the atomic number, take away 2. Okay, so this new element would be have a mass number 4 less than the original, and an atomic number 2 less than the original. So if we started off with, say, A was 42, so this element had a mass of 42, and say it had an atomic number of 21, the 42 would change to 38, and the 21 would change to 19. Okay, just for example. Beta emission, we'll start with our X. Okay, now the A stay the same, so the mass number stays the same, but our Z increases by 1. Okay, because our neutron is converted to a proton and the electron being ejected, and so we have 1 extra proton. So all you have to do is you just add 1 to the atomic number. So if this was 42, 21, again, this would remain at 42, but this would be 22, okay, with a beta emission. Positron emission, okay, we sort of go the other way. We start with element X, mass number A, atomic number Z, and now we have a proton which is being converted to a neutron and this positron particle, this very small positron particle, and so now we have 1 fewer protons, but that's compensated by a neutron, and so the mass stays the same, so A will stay the same, but we have 1 fewer protons, so our atomic number goes down. So this again was 42, 21, this would be 42, but now it would be 20, okay, 1 fewer for the atomic number. In gamma emission, nothing really happens except we lose this M, which is just a convention to indicate that the element's excited. And so this would just stay the same. Now we come to an important concept such as half-life. Now half-life is one of the ways that we date things. It's very useful. These radioactive elements, they decay via a first order process, and we measured this via a half-life. And so a half-life is the time that it takes for half the material to decay. Okay, so let's have an example with phosphorus-32. So phosphorus-32 has a half-life of 14 days. If we start with 100 grams, then, so initially on day 0 we have our 100 grams, then after 14 days that will be down to 50. After 28, which means another 14 days have passed from the original, we'd be down to 25. After 42, which is another 14 days, we'd be down to 12.5 grams. So what it means is that every 14 days we have half of the remaining material decaying. So let's have a look at some calculations, and I sort of made up a formula here. If A is the amount, O is the original amount, and then we have 0.5 to the power of number of half-lives. Okay, so in your text you would see that you just keep multiplying a half times a half times a half for the number of half-lives that it is, and that's sort of the same as raising this to a power. So I guess just to show how this would work. So say I want to know the amount of material, go back to our example with phosphorus-32, the amount of material that I would have after our 42 days. Okay, so I'd have to work out the number of half-lives that have passed, and so I do that by looking at my table. And so after 42 days, there'd be 1, 2, 3 half-lives have passed. Okay, the easiest way to work out the number of half-lives is to get the days or minutes or whatever units it's talking about. In this case, it's 42 divided by the actual half-life, 14. Okay, so it'd be 42 divided by 14. That's 3. Okay, does that make sense? So say if something had a half-life of 20 minutes, and you want to know how much is left after 78 minutes, you'd have 78 divided by 20, and that would be 3.9. So that's how many half-lives have occurred, and you'd need that number for this calculation. So if we use the 42 days, then we'd know that we've gone through 3 half-lives. So using this formula, the amount I'd have left would be the original amount, which would be the 100 grams, times 0.5 to the power of 3. So it would be 100 times 0.5 to the power of 3. That would give us our 12.5 grams, which is what we had on that previous table. So 3 is obviously a nice, neat number, but just to show you, so that's what we had on that previous table, 12.5 grams. So 3 half-lives is a nice, neat number, but it's not always, the questions aren't always going to be as such. So let's have a look at another example. So given the half-life of phosphorus-32 is 14 days, and we start off with 100 grams, what would be the mass of phosphorus-32 after 91 days? Okay, so we'd first calculate our number of half-lives, which would be the 91 divided by 14 is 6.5 half-lives. Okay, so just again, this is the number of days that the question's asking about, and this is the half-life. And so you can calculate how many half-lives you have, which is 6.5. And so then using my formula, the amount that I'd have after 91 days would be the 100 grams times 0.5 to the power of 6.5. Make sure you can do this on the calculator. So if you have a calculator, try and use it now to get this answer. So hopefully you will get 1.1 grams. If you cannot use your calculator to get that answer, then there's something wrong. And I'll show you quickly on my calculator how it works. So it would be, just try to get no glare, 100 times 0.5, and I'll use this XY button on my particular calculator, and it would be 6.5. Okay, and we should get 1.1 grams. Okay, so make sure you can do that calculation on your calculator. Just to do another quick example. So the half-life of lead 191 is 1.33 minutes. You know, sometimes half-lives are fractions of a minute or even just a fraction of a second. Sometimes they're billions of years. Some radioactive decays, you know, have half-lives of billions of years, or at least millions. And so the half-life varies a lot. But let's have a look at this 1.33 minutes for a half-life. How much lead is left when 37 grams of lead 191 decays for 25 minutes? Okay, so that's quite a lot of half-lives, 25 compared to the 1.33 here. So our first part of the calculation will involve calculating the number of half-lives. So it'll be the 25 minutes divided by the 1.33 minutes, which gives us 18.80 half-lives. Again, don't round this stuff. Okay, so you might want to, if you do that calculation, you might want to put this in the memory. Okay, in the memory in the calculator. The previous question where it was 6.5 for the number of half-lives, that just worked out to be a nice, neat number. But this will work out to be 18.8 something or something like that. And you'll need to put that in your memory, because if you round off here, you get a round-off error in the final answer. So using our formula, we have the original amount times 0.5 to the power of n, which is the number of half-lives, so it'd be 37 grams times 0.5 to the power of 18.80, and that comes out a very small number, 8.1 by 10 to the minus 5 grams. Again, make sure you can do these calculations. And we'll just leave it there for today.